Well, thanks for the invite to be here. It's my pleasure. My name is Mike Sullivan. I'm the CEO and co-founder of Bay Minerals. I'm here with my partners. I'm going to see if I can operate this. So we upcycle value from mine waste, and we basically focus on large tailings. So who are we? Well, we're a unique team. I think this thing is a... didn't work very well. Okay, so who are we? A unique team with a unique value proposition. I'm here with my co-founder, Ms. Trina Barrett. Trina's been in born in Bayvert. Family has a long history with this mine in Bayvert. I'm also here with Alan Cram, who's one of our directors, who is very knowledgeable in innovation in the mining space. We also work with RPC. This, actually, I apologize, it didn't come out the way it's supposed to, but Leo Chung is here. RPC does most of the research and development for us. We work with the College of North Atlantic, Guy J. Bailey. Scott Bailey is a part of the company, and ACOA, National Research Council, and the X Prize Carbon Removal. Okay, this one worked out better. So what do? We take mine waste, we apply our sustainable technology, and we extract decarbonized minerals, and we get carbon credits. And we essentially monetize it with these two value propositions. This, what we're looking at with our Canadian beachhead, is a world-scale waste site. Bayvert's interesting. It's the oldest mining district in North America. There's 22 past producing mines. And I believe that the Advocate asbestos mine in Bayvert was the largest mining operation in the island of Newfoundland. And as it got orphaned, it left a very big waste pile site. So you have ultramafic waste rock, about 250 million tons of it, and you have a chrysotile tailings, about 50 million tons. And it contains a fair amount of asbestos, and it's a toxic material, and it's what we're going to solve. So anytime you're developing a technology, you have to identify what problem you're solving. And the problem we're solving in Bayvert is the orphaned chrysotile mine, the tailings, which is an asbestos mine. It's a carcinogenic material with respiratory toxicity only. And then there's acid mine drainage. It's very visible. It's in the area. And I'll explain why the two of them sort of offset each other. The acid mine drainage is very visible. It's bright colored. It's ongoing for hundreds of years. It's a problem that there isn't a real solution for right now. It's toxic to nature, so it's basically not good. It's, and I'll show you in a minute what happens when it goes into the ocean. So it's very colorful. It's a color of the rainbow, really. So you can tell the pH and the toxicity of it by its color. So when acid mine drainage is a pH of 2, it's bright red. It can actually be negative pH, and all the metals are very soluble in it. And as the pH comes up, the color changes. It goes from red, orange to yellow. This is what's happening in the Bayvert area. From Southbrook, it's going into the Bayvert Peninsula. It's dropping all the metals in there. It's acidifying the ocean, and it's basically, it's not a good thing. There's metal pollution from it as well. So why is this important to us with the asbestos mine? So the asbestos mine is highly alkalinic. Its mine waste is a high concentration of magnesium oxides, about 39%. You can tell by the color of the water, it's highly alkalinic water here. The pH is high. These two pits, they excavated about 200 million cubic meters, very, very large. And what's left on surface are these tailings, and they're ultramafic mine waste in the form of the waste rock, which is about 250 million tons. The asbestos tailings are around 50 million tons, so it's very, very large. Here's what we do. We have a mined waste solution. So we take the low pH acid mine drainage. We're going to be collecting it, treating it, taking out the gunk. There's minerals in it that aren't of high value. We take the pH fluid and we apply it to our technology. And the chrysotile and the ultramafic mined waste is very high pH. So we get three things. We get critical minerals from it. We get carbon credits from it. So we mineralize the carbon and we neutralize the pH. So on our path to commercialization, we've taken this thing extensive research and development. More than 5 years of work has been put into this by our group. So we've got proof of concept in the lab, we've established our IP, we have customer traction, and we've taken this thing from a TRO level of 0 to 6. We're at pilot demonstration stage. We're happy to say that we're fully funded now. We can build this thing, and it will be built. I'll explain it to you in a minute. But once we build the pilot plant, we can take this to the commercial stage. We can either go in a scalable modular plant, or we can go into a world-scale, larger plant. We have the resources to do it. The pilot demonstration plant is going to be 1,000 kilograms. We have environmental approvals to go ahead with this. It's going to be done in batches of 20 to 50 kilograms. It's going to be located at the College of North Atlantic's campus. We're fully funded. We expect to be operational 2025. This is a process flow diagram. It's probably not that meaningful, but one of the things that we're adding to this is this ultrasonic cavitation process. And to explain the technology when we upcycle, we start with the chrysotile fibers. We run it through this process called ultrasonic cavitation. It's used in agriculture, it's used in the medical profession. It's not very widely used in the mining industry. And one of the reasons why it's optimal here is because this stuff has a low grind index and doesn't respond to being ground down to a small size. The ultrasonic cavitation is a wet process, and it optimizes that. And so what we end up with is a lot of asbestos removal, but it optimizes it to go into the acid leaching. So when we take this from how do we extract the minerals and get rid of the asbestos fibers, we essentially convert the structure from crystalline, it's a crystal structure, to amorphous. It makes it fiber-free. We have a proprietary mineral extraction process. We liberate the industrial minerals, some battery metals, and we get CO2 credits. And I always want to explain to people like what asbestos is, because in demystifying it, it's very simply magnesium and silica bonded together in a crystalline sheet structure. It creates a hair-shaped fiber. So we've identified it at the microscopic level. What we do is we eliminate that crystal structure. We render it harmless and liberate the minerals. So how do we know this? Well, we've got extensive testing and extensive verification. We use SGS. They have a transmission electron microscope. So we take it right down to the microscopic level. So you can see in the middle picture there is the chrysotile fiber. So that's the dangerous stuff. And at the end of the process, it's granular. So it's totally removed. It's totally detoxified. We are a circular economy business model. So this is a waste to value business model. We take two forms of mine waste, acid mine drainage. We apply it to the chrysotile tailings. The extractive technology, it produces decarbonized minerals. There's a high product market fit. So we have identified all the markets that use this. They go into sustainable markets like fertilizers, tires, batteries. And just to show you what the decarbonized minerals are, and a lot of people don't focus on industrial minerals, but they have extremely high value. The markets are very big. Magnesium oxide gets about $700 a ton. It's used in net zero cement. The market's big. Magnesium sulfate's another product that comes off of this. It's used in the fertilizer industry. It's an even bigger market. They'll buy all of it they can get. The Silica goes into the green tire market, nickel goes into the battery market, and we produce carbon credits. And the value proposition is relatively high. And the yield is high. That's what makes it very worthwhile. So we get more than 75% yield in these industrial minerals. But the other thing is there's a critical mineral component to it. It's 0.22% nickel cobalt. So if we were to look at just the tailings, there's close to 250 million pounds. But if we used all the ultramafic rock to extract the nickel out of it, nickel cobalt, we get a 1.5 billion pounds coming off it. So, this is waste of value at an extreme. The carbon sequestration is something that actually works very well. We know this works because they're doing the same thing in Quebec with the asbestos tailings. What we do is we're going to take the waste rock and we're going to heap leach it with the acid drainage. And what that does is basically it liberates the reactive portion of the magnesium and makes it the ability to carbonate it. We call it mining for carbon credits. There's also another component to sustainability with the carbon credits, because right now the acid mine drainage is going into the ocean. It's acidifying the ocean, depleting marine carbonates. It off-gasses CO2. So you end up getting a carbon avoidance credit or a reduction credit. They're not the high-value carbon credits. But when we divert the acid mine drainage to the ultramafic waste rock, we get carbon mineralization, we do the acid leaching or the mineral leaching, we alkaline the waste rock, and these absorb CO2 where you can get carbon removal credits, and eventually it goes back into the ocean as an alkaline enhanced material, and again, it improves marine health. This is what we do with the carbon mineralization. If you look at the green side, this is what happens in nature. Carbonic mineralization happens slowly over time. The acidity of acid rain, the CO2 in the air combining with rain, when it hits alkalinic waste rock, it liberates the alkalinic material and it carbonates in nature. We're enhancing it by taking the sulfuric acid that comes off of the acid mine drainage and accelerating that process so we can speed this up in real time. Okay, some of the stuff isn't working very well. Why is this valuable? Well, carbon credits are worth $810 in surfacial mineralization. I apologize, there was a nice looking chart here, but it looks like it's not there anymore. Okay, what's the Newfoundland advantage? Well, this only works on ultramafic rock, and ultramafic rock is only 1% of the Earth's surface, but it's 100% of the rock in Newfoundland. So Newfoundland's got this really big advantage. The chart that you see below, the map where the acid mine drainage is, so we've looked globally where all the acid mine drainage is coming from either nickel or copper or lead zinc mines, drainage, and mapped it against where ultramafic rock exists on the surface of the Earth. Newfoundland is one of those spots. Europe has got a fair amount of it too, but it's not, this is a unique value proposition for Newfoundland. What we're doing is we're putting Newfoundland on the map. This is the first carbon credit project in Newfoundland. This is from the X Prize carbon removal competition that the Musk Foundation has put on. So they've registered us for this project. We're accepted into the program and it works. So what we want to do is put Newfoundland on the map, not only for things other than its minerals, but also for the carbon credits. This is a high ROI business model. We can do it large scale, large volume. It's low risk. We're taking mine waste. We don't have to explore or mine anything. The environmental permitting is surprisingly low because there is no environmental impact. We're actually improving the environment. The execution risk is low. It's a passive CO2 mineralization. It has high environmental benefits, waste mitigation, improving health and safety, but there's a big community benefits program associated with this that will actually help the Bayvert community. So why now? We've built a strong business case. It's a for-purpose, for-profit business model. The technology is ready. It's a solution for pollution. It's a viable waste-to-value business model. The market's ready. We've got customers. It has very robust economics. But more importantly, the resource is ready. It's a low-cost supply of mine waste. It's low risk. It's in a strategic location with lots of competitive advantages. We take mine waste, we apply green technology, we make sustainable resources, we improve the environment, and we make money. Oh, there's Alan. What are you doing there? It got